All right, let's talk about something you use every single day, probably without even thinking about it: coordinate geometry. Now, I know it sounds a little intimidating, right? But it's actually the secret language that powers everything from the maps on your phone to the ride-sharing apps you use. We're going to crack the code on it today.
So, to get our heads in the game, let's start with a little puzzle. Imagine you're looking at a huge, totally blank wall, and you stick a tiny dot somewhere on it. Now, you have to call your friend and tell them exactly where that dot is, so they can walk right up and point to the same spot. How would you do it?
You'd probably say something like, "Oh, it's kind of in the top right." But think about it. That's not very helpful, is it? Is it a little lower? A bit more to the left? That kind of vague description is a recipe for confusion. For things that need to be exact, like a map, we need something way better. And this is exactly the problem that a brilliant French mathematician, René Descartes, tackled centuries ago. He realized that words just weren't going to cut it. What we needed was a system, a universal, reliable map. And his solution was just elegant. So how does this map get built? It's so simple. Let's do it together. First, you just draw a number line going side to side. That's our x-axis. Then you draw another number line, this one going up and down, and you make sure it crosses the first one right at the 0 mark. That's our y-axis. And that single point where they intersect, that 0, 0, that's our starting point for everything. It's called the origin. And just like that, with two simple lines, you've created what we call the Cartesian system. It's this beautiful grid that lets us pinpoint the location of anything on a flat surface using just a pair of numbers. And we call that pair of numbers its coordinates.
And I'm telling you, this is not some abstract thing you only see in a math class. It is constantly working for you. When you order some food or call for a car, your phone isn't telling the driver, "Hey, I'm kind of by that one building." No way. It's sending a super precise set of coordinates, an exact address on this giant invisible map, so they can find you, no problem.
Okay, so you see a point on the map and it's labeled, let's say, 4, 2. It seems simple enough, right? The first number is x, the second is y. But what do those numbers truly represent? The answer is kind of surprising, and honestly, it's the key to unlocking this whole system.
Now, here it is. This is the big aha moment. Most of us think the x value just means go right this many steps, and y means go up this many steps. And while that gets you there, the real secret, the more powerful way to think about it is this. The x-coordinate is actually the point's distance from the vertical y-axis, and the y-coordinate is its distance from the horizontal x-axis. It's all about the distance from the other axis. Get that? And you've got it all. Now, you know, mathematicians, they've got to have a formal name for everything. So the official term for that x-coordinate is the abscissa. It's a fancy word, but it just means one simple thing. How far is your point perpendicularly from that main vertical line, the y-axis? And you guessed it, the y-coordinate has its own fancy name, the ordinate. And again, it's just asking a simple question. How far is your point from the main horizontal line, the x-axis? So the abscissa and the ordinate, those are the two pieces of the puzzle that give every single point its own unique address.
Okay, so these two axes don't just help us find points. They also do something else really useful. They chop up the entire map into 4 distinct zones, and these zones are called quadrants.
And what's really cool is that there's a super simple pattern to them. We start in the top right, that's quadrant I, where both x and y are positive numbers. Then we just move counterclockwise. In quadrant 2, x flips to negative, but y stays positive. Down in quadrant 3, they're both negative. It's this perfectly logical system, so the signs of the numbers instantly tell you what neighborhood your point lives in.
So what happens if a point isn't in a quadrant, but it's sitting right on one of the axes? Well, that little distance secret we learned makes this super easy. If a point is literally on the x-axis, what's its distance from the x-axis? It's 0, right? So its y-coordinate has to be 0. And the exact same logic works for the y-axis. Any point on it has an x-coordinate of 0. Simple. All right, let's wrap this up into your official mission briefing. The 3 core rules you need to remember. First, you always start at the origin, 0, 0. Second, remember x is your horizontal, y is your vertical, and third, the master key, the big secret. The x-coordinate is the distance from the y-axis, and the y-coordinate is the distance from the x-axis. That's it. That's the whole game. So let's end with one final mission to put your new skills to the test. Imagine a point is located at 3, -2. Now, picture the vertical y-axis acting like a perfect mirror. Where would the reflection of that point show up? What would its new coordinates be? Think about which distance changes and which one stays the same, and you'll know you've really cracked the code.